In this problem, we've been given the function f of x and asked to find the local max and local min points. Notice that this time our f of x function is not just a simple third-degree polynomial. This time we have one linear function, 7x, times another log function, ln of 0.05x, and then we're adding to that constant, 500. So this is not your easy third-degree polynomial to deal with, but we are going to walk through the same procedure. I'm going to go through this problem in two different ways. First, I'm going to use Excel to help me with the problem solving, with the equation solving, and then I will show you how you can actually solve this equation relatively simply by hand. But in this class, in business calculus, I would allow you to use Excel and Solver to actually solve where the derivative equals 0 on a problem like this. All right, so the function f of x is given. To find local max and local min, we know we have to first identify critical points. So that means we need to identify where f prime of x is undefined and also where f prime of x is equal to 0. So first we better find f prime of x. Note, f of x, the first term, is a product. One function 7x times another function ln of 0.05x. So to find the derivative of this first term, we need to use the product rule. We're going to do f prime g plus f g prime. This is just to find the derivative of the first term. Then we need to add on the derivative of the second term, but the derivative of 500 is just 0. So I don't really need to worry about that. I only need to find the derivative of this first term. So the derivative of 7x is 7 times the original second function, ln of 0.05x, plus the original first function, 7x, times the derivative of ln of 0.05x. The derivative of ln of 0.05x, that's going to require the chain rule. We think of it as ln of t, so the derivative of the outer function is 1 over t, which is 1 over 0.05x. That's the derivative of the outer function. Times, we have to multiply by the derivative of the inner function, the derivative of t. T is 0.05x, so the derivative of t is 0.05. So there is the derivative of the inner function. We definitely can simplify this thing down. So I note here the first term, I have a lot of parentheses that are absolutely unnecessary. 7 times ln of 0.05x can just be written 7 ln of 0.05x like so, plus 7 times x times 1 over 0.05x. So notice x in the numerator cancels with x in the denominator. And notice 0.05 in the numerator cancels with 0.05 in the denominator, leaving 7 times 1, so just 7. At this point, I'm going to make a couple notes about our domain. The function f of x, the original function f of x, is only defined for x greater than 0. And the reason for that is that the only values that can be plugged into natural log are values bigger than 0. So when I plug in x is bigger than 0, it will be defined. If I plug in x equals 0 or x negative, it won't be defined. The original function. So when we're asking about the derivative of that function, I only need to consider values in the domain of the original function. Only consider x is greater than 0. So when I think about critical points, and I ask, where is f prime undefined? I see here f prime is also undefined for x equals 0 and undefined where x is negative, but I wouldn't call those critical points because those are not x values on the original function. So notice, x greater than 0 is still the domain of f prime, and that is the same as our original function. There aren't any positive x values where we're going to find undefined derivative values on f of x. So I don't need to worry about f prime of x undefined type critical points. Doesn't happen. Instead, I can focus on identifying where is f prime of x equal to 0. So I set 0 equal to my derivative. And like I said, I'm going to go ahead and have Excel help us with this. Excel Solver is going to help me solve this, and then I'll show you how you can solve this pretty easily by hand. All right, in Excel, I have put some x values in column A. I've put the actual original function, 7x ln 0.05x plus 500, into column B. And in column C, I've put our simplified f prime function, 7 times ln of 0.05x plus 7. Now I selected some x values, an x value close to 0. Remember, you can't plug in 0, you can't plug in negative, so I picked a little decimal, 0.5. And then I went up by units of 0.5. All right. What I'm noticing here in my derivative values is that the derivative values are negative here. I've highlighted in red. And then suddenly the derivatives change to positive here, which I'm going to highlight in blue. Must be the case that somewhere between x is 7 and x is 7.5, the derivative actually equals 0. So I'm going to put my cursor in one of these two. It actually doesn't matter. I'll just go ahead and put it here at f prime of 7.5. I'm going to use Solver. I want Solver to help me find when cell C16 equals a value of 0 by changing the x value cell here. So cell A16. I hit solve. All right, mine's giving scientific notation, negative 1.5 times 10 to the negative 8. So essentially that's 0. I'm just going to actually write 0 there. When x is 7.357589 approximately, the derivative is 0. So this is my critical point at x equals 7.35, I'm going to say about 8. Just rounding it a little bit there. Right, I notice before that critical point, f prime of x is negative, so f of x is decreasing. And after that critical point, f prime of x is positive, so f of x is increasing. Notice the nice thing about doing this in Excel is it actually is showing you the first derivative test right here in column C. It's already tested an f prime value on the left interval, tested an f prime value on the right. This is a minimum because at that critical point we have a flattening of f of x. On the left side f is decreasing, on the right side f is increasing. So we can now just look at this and see f of x has a local min at that point. So Excel helped us solve that. The sort of thing I would expect you to write down in your write-up of this is explaining to me, I use Solver to identify where the derivative equals 0. You tell me the cell number where I can see that. Next, you should also go through your first derivative test argument to demonstrate that you know that this is a local minimum. Now the work, the calculation for that is shown in Excel, but you still need to make your argument for why you know that this is a local minimum. We know it's a local minimum because on the left side of that critical point, f prime was negative. On the right side of that critical point, f prime was positive. Therefore, we can conclude f was decreasing, then flat, then increasing, so it's a local minimum. And we can see all that in column C. So this is the sort of explanation you would need to give and also attach your Excel file so that someone could look at that and see the argument being made for this being a local minimum. All right, in case you would like to solve this sort of equation by hand, that is fine. I did want to show you how to do that as well. So it's the same, of course, solution that we're going to get here, but I'm going to go back to the step where we had our derivative. 0 equals 7 times ln of 0.05x plus 7, and just show how you can actually solve this by hand. So first of all, you would subtract 7 on both sides. We're trying to isolate x here, so I'm bringing this 7 over to the left side. I would then go ahead and divide both sides by this 7. So I have negative 1 equals natural log of 0.05x. Remember, if you have ln of a equals b, you can rewrite that in exponential form e to the b equals a. And that is exactly what I have here. ln of 0.05x is negative 1. I could rewrite that as e to the negative 1 is equal to 0.05x. So to solve for x, I divide both sides by 0.05. This actually gives the exact value of the critical point. But if you pull out your calculator and round this value, e to the negative 1 over 0.05, you get about 7.358, just as we got in Excel. And then you could do your first derivative test and make the same argument that it's a local minimum.